cannot hear my voice. Let's see. Can you hear me? I think nothing is wrong here. Okay. Okay. This recording will be deleted in 40 after 40 days. 14 days, yes. So after that, you cannot watch this video on Canvas, but I will upload this to YouTube, so there you can watch in any time. Okay. Any questions so far? I mean, I don't delete this video on Canvas, but it is deleted automatically, so I cannot do anything about it, unfortunately. Okay. All right. So let's consider one simple, very simple example. Again, consider coin tossing problem. So our favorite example. And let's say uh, this sigma algebra is the power set. So we define somehow a probability measure that satisfies the axioms of probability. Okay. So for example, we can define this as the cardinality of event divided by the cardinality of the sample space. Okay. And of course, the cardinality of sample space is 2. And the cardinality of this A, A is one of these 4. So it cannot be greater than 2. Okay, so it satisfies the first axiom. If we define probability in this way, if this A is empty set, it's 0. If this A is either this H or this T, then A cardinality is 1, so it will be 1/2. If this A is omega, then this probability is 1. So first axiom, this is satisfied. Okay. The second axiom was if we plug in omega itself, it should be 1, right? In this case, it is omega cardinality 2, which is 2 over 2, which is 1. Yeah, so the second axiom is satisfied. And third axiom, third axiom says if there are infinitely many sets, elements of F, then their countable union. And also, there should be disjoint, right? AK intersect AL should be empty. If K is not L. Okay, disjoint. Then probability of the union of these events is the sum of probability of these events. So does this hold for this probability? There are only 4 elements here, but this so there are not infinitely many events in our example, but nobody says these are redundant, so we can choose, uh, let's say, choose some element. For example, uh, as a matter of fact, we can choose empty set many times, infinitely many times. Okay, so let's say A1 is empty, A2 is empty, and everything is empty. Then they are always disjoint, right? Because everything is empty, so any pair, if we take the intersection, it's empty. In that case, the probability, if this is the case, okay, the probability of this countable union is, they are all empty, so this union is also empty. The cardinality of empty set is 0. So this probability is 0. Okay? And is this equal to this summation? So this is the probability of empty set. And the probability of empty set is 0. So if you add 0 infinitely many times, it's 0. So this is equal to this. So if this is the case, the third condition is satisfied. Okay. Now, let's say A1 is omega itself. Then, what can be A2, A3, A4, and so on? If this A2 is anything other than empty set, then A1, okay, suppose if A2 is not empty set, then intersection between A1 and A2 is not empty. But that is not our assumption, right? Our assumption, they must be disjoint. So the only way we can make these subsets disjoint is that to choose every other sets to be empty. Okay? So if one of these A1, A2, A3, and so on is omega itself, then everything else must be empty, okay, to satisfy the assumption. If that is the case, then, not this one, the probability of the countable union is omega union empty union empty union and empty. So however many empty sets are there, this union is omega itself. Therefore this probability is 1. Okay. On the other hand, the sum of probabilities of these events is this. So A1, A2, and so on, which are A1 is omega, A2, and so on, they are all empty. and this probability of omega is 1, and everything else is 0. So the result is 1. So therefore the left hand side is equal to the right hand side. So if this is the case, the third axiom of probability measure is satisfied. What about other cases? If A1 is H, then A2, A3, A4, etc., they cannot be omega, right? Otherwise, they are not disjoint. The only possibilities are either tail or empty set. Okay? So if A1, A2, A3, and so on, they contain at least one H and one T, then everything else should be empty set. So, of course, A2 can be H and A1 can be T, or A5 can be H and everything else. We can swap the order, but the point is only one of these subsets is H and only one of these subsets is T. Everything else must be empty. Otherwise, we cannot satisfy the condition of disjointness. Okay, if this is the case, then the probability of the countable union of all these is this. Probability of, so union of this and this and this and empty sets, it's omega. The probability is 1. Okay, and probability sum of probabilities of these events is this. Plus D plus B empty plus empty plus all empty. So this is 1/2 and this is 1/2 and everything else is 0. The result is 1/2 plus 1/2 plus 0 is 1. So the left hand side is 1, the right hand side is 1, so they are equal. Therefore, the third condition is satisfied in this case. And I think there are no other possibilities, right? Are there? So, these cover all the possibilities. So in any case, we have seen that the third condition for probability measure is satisfied. Therefore, the probability measure defined in this way, defined in this way, satisfies the axioms of probability measure. Okay, so it's a probability. All right.